So in this video, we're going to talk about function operations, addition, subtraction, multiplication, division, and composition of functions. And honestly, this first part, I really don't even think I need to give you examples on, but I will give you a quick example of each. The big thing that I want to talk about, though, if you read this main question, it says, how do you combine, multiply, divide, compose functions, and how do you find the domain of the resulting function? So that is like the big thing I want to talk about on the front end. So if we talk about adding functions, f plus g would literally mean just to add these two polynomials together. So the resulting f plus g for this one would be x squared minus 2x plus 6. Or if we did f minus g, remember when we do f subtraction, that the negative sign is going to change the signs of the second function there. So this is going to become minus x squared plus 5x minus 2. So the result there would be negative x squared plus 8x plus 2. Now, the domains of these original two functions, this one is linear, and this one is quadratic, and the domains of both of those are going to be all real numbers. So because the domains of the original functions are both all real numbers, then the domains of their sum and differences are also going to be all real numbers. So this is what I would write down for that statement about how you assess the domain of addition and subtraction. All right, in this example, we're going to talk about multiplying. So again, I think that you already know how to do the skill. My focus is to talk about the domain. So this says the price is X and the demand is 5,000 minus 10X. We want to talk about revenue. So let me go ahead and write some things down. So if we perform the actual operation, P of X times D of X, this is the result that we get. So now let's talk about how the domain is affected, because when we're talking about word problems, the domain is affected even if the functions we're talking about are linear or quadratic or otherwise. Okay, so for instance, if we think about what these functions are talking about, price is something that needs to always be positive, which means that in this instance, X, or the domain, is always going to have to be something that is greater than 0. They're not going to sell something for less money, right? Demand also needs to be something that is greater than 0. So in this case, 5,000 minus 10x needs to be greater than or equal to 0. Well, if we solve that out, negative 10x is greater than or equal to negative 5,000. Sorry, I'm running out of room here. And then if I divide by negative 10, that's going to mean that x is less than or equal to 500. So if one domain has to be greater than 0 and the other domain has to be less than 500, then the resulting domain for P of x times D of x would have a domain of between 0 and 500, or a domain 0 less than or equal to x less than or equal to 500. So it is only defined on that specific domain. Outside of that, the context doesn't make any sense. All right, so dividing functions. If I go to set this one up, this is going to say f divided by g, so x minus 7 over 2x squared minus 13x minus 7. Now, we have learned to divide the other way. If I divide by 7, I could do synthetic division. But in this case, I can't really do synthetic division. This doesn't work for that. So instead, what I'm going to do is I'm going to factor each one of these polynomials. So remember, this bottom trinomial is going to factor, just like X game, bottoms up, multiply to give you negative 14, add to give you negative 13. It's going to be negative 14 and 1. Remember that because we multiply by this 2, we have to go back and divide by it. I'm going to write this how we normally do. So x minus 14 over 2 and x plus 1 over 2. That will give me x minus 7. And remember, bottoms up, this is 2x plus 1. All right, so if I put my function back together, this is now going to say x minus 7 over x minus 7, 2x plus 1. And you might notice that since these are x minus 7 on the top and the bottom, those will actually cancel with each other. So that will simplify. But we can't just have nothing on the top. So remember, something divided by itself is 1. So this is really going to give me a result of 1 over 2x plus 1. Now this is the result of the division. So that is how we divide polynomials or divide functions. But what I also want to talk about is how do we restrict the domain. So for rational functions, or for division, the domain is restricted where the denominator cannot equal 0. All right, so make sure you have that written down. And then let's look at this example specifically. So the denominator in this example factored to end up being 7x, I'm sorry, I said that wrong, x minus 7 or 2x plus 1. Well, I want this to not equal 0. So I'm going to do this just like we do when we find solutions, except these are not solutions. So I'm going to set this not equal to 0, not equal to 0. And if I solve that, that's going to tell me that x cannot be 7, and also x cannot be negative 1/2. So my domain for this result is all real numbers except, so we can write that as, this is set notation, it would be all real numbers not equal to 7 or negative 1/2. Or sometimes they say excluding instead of not equal to. So this last concept we have to talk about is called composition of functions, which is really like functions within functions. So there's a few ways we can see this written. We can see this written as f of g of x, or we could go the other way around. It could be g of f of x. They can also note this as f, this is like a little circle on the inside, f of g or g of f. So that circle almost looks like a multiplication dot if you're writing it in your notes, but it's an open circle right there in the middle. So let's look at a few examples of how we actually operate with compositions of functions. Okay, so in this first example, we're being asked to find f of g of 5. So first what I'm going to do is find g of 5. So we kind of work inside out on these. So if I wanted to find g of 5, then I would plug 5 into the g function, which would be 5 plus 1, so that is 6. So then now I would be finding f of 6. And so I would plug 6 into the f function and evaluate. That would give me 6 squared. So f of g of 5 equals 36. All right, if we do the same thing with this other function, this time it tells me to find f of 5 first. So I would do 5 squared first, which would be 25. And now I would do g of 25, which would then be 25 plus 1 or 26. So g of f of 5 is 26. With these, we can also create new functions. So this example is asking me to find f of g, and just like when it's written in the other format, we kind of start with what's on the right first and substitute that into what is happening on the left. So in this example, we would write this as, I'm plugging the x plus 1 in to the x squared equation. So that would be x plus 1 squared. And then if I worked that out, you all know we have to write that twice. And I'm going to skip the steps for us here, but this ends up being x squared plus 2x plus 1. Now, when we talk about domain for these, just like honestly with any of the other functions, if either function is limited, then that's going to impact the domain of our composition. But since neither one of these is limited, right, I have linear, which is not limited, and I also have quadratic, which is also not limited, then that means my result, which you can see here is another quadratic, is also not going to be limited in this example. So we just have to verify if any of our initial functions are limited, then our composition or operation or whatever it is we're doing will also probably be affected by that limitation.